In this chapter, we'll discuss functions or procedures in the functional programming paradigm. Starting in this video by talking about procedural abstraction in a little bit more detail than what we've done. And we'll start today by looking at an example problem that will help root our discussion, so to speak. And that example is finding the square root of some number. So the square root of a number is defined as follows. The square root of some number x is equal to y if y times y, or y squared, is equal to x. And that gives us a declarative definition of square root. It tells us what a square root is, but it doesn't necessarily tell us how to find the square root of a value. In order to do that, to get the procedural type knowledge here, we could use one algorithm known as Newton's method of successive approximations. So the general idea of Newton's method is to guess, and then check, and then improve. So we'll start with the input number x, the value that we want to square root, and some guess for what that square root might be. Just for simplicity, we'll assume our initial guess is 1.0. Okay. Now, if the guess is good enough, if it's close enough to the correct answer, great, we're done, no more troubles. But if it's not, then we need to improve our guess a little bit and then repeat the process over. So check and improve, guess, check, and improve over and over again. Okay. So the improve step is done by the equation as shown here. To get a better guess, we're going to average the current guess y with the quotient x divided by y. And the reason this works is that if we have x divided by the square root of x, well, that gives us the square root of x, right? 25 divided by 5 is equal to 5. So it's a bit of a stable point in this process. If our guess is too big, then we'll get a value that's smaller, right? If the value on the bottom of this quotient is too large, then we'll divide by too much, and our new guess will be a little bit smaller. If it's too small, then this will be too small here, and the result will be a number that's slightly bigger than the square root. So our guess is going to get closer and closer with each improvement, regardless of the current value of that guess. So as an example, if we wanted to compute the square root of 2, we'd start with a guess of 1.0. We'd check to see if that's close enough. It's not close enough as far as I'm concerned, so we get a better guess. So we take the quotient of 2 divided by 1, and then we average that. So we average the guess of these two things, so x divided by y, with the current value of guess, and divide by 2 for the average. We get 1.5 is our new answer. So that's our new guess. We say, is that close enough? And we'll say it's still not close enough. So we continue to improve. So 2 divided by 1.5, 1.5 is too big, so we get a value that's smaller than the square root. And then we average between those two, and we get a little bit closer. Again and again and again, you can see that the values here get closer and closer to the true square root of 2. Now, the code to create this algorithm, or to run this algorithm in the Scheme algorithmic language, could look as follows. So I'll provide this code here, and there's a bunch of different functions here. So the process itself spans many separate procedures, and the problem, the idea of square rooting a value, is decomposed into many simpler subproblems, like improving the value, determining if it's good enough, and repeating. So there's a bit of a separation of concerns, or a divide and conquer, which simplifies our effort when trying to design and test all of these applications. Then the solution, the overall square root process, is defined by the interaction of all of those smaller modular components. So to get an initial understanding of this program, it'll help to see the decomposition tree. So let's go to a whiteboard here. Now the program is defined in terms of many functions, but the main function is this square root function. That's the one the user is going to type in order to get their code square rooted. So we'll say sqrt at the top of our tree here. Now square root is dependent on square root iterations, so let's draw a line and we'll say sqrt iteration. Okay. Now in the body of square root iteration, we can see it calls good enough, it calls improve, and it also calls itself. So it's a recursive program. We'll come back to the notion of recursion for now. We'll just take a look at the branching of code for this point. So square root iteration calls good enough, question mark, and it calls improve. It also calls itself, so if we want, we can draw a little loop there. Right. Now in those, we have good enough, which is dependent on ABS, which is a built-in absolute value function. But I'll put it here anyways. ABS. It's also dependent on the square function. Oh, why didn't that work? SQARE. And the improve function's dependent on this average function. So we say average over here. And that's pretty much it. Square is dependent on times. I won't include all the arithmetic operations, but those are in there as well. So the entire program breaks down somewhat like this, and this might help you see how all of these sort of interdefined pieces come together to create the overall square rooting solution. So the code itself says square root some given value, which calls squared iteration with 1.0 as the initial value of guess, and x would be the value the user passes in. And the code says if it's good enough, so if the current guess is close enough to the square root of x, then we'll return the value of guess. If not, then we'll call improve on our guess to get a better guess and pass that into the next step of this square root iteration program, the repetitive loop. Again, we'll talk about the repetition, the recursion later on. For now, functions are calling other functions is the important thing. So in order to improve a function, we need to essentially use the calculation up here, or I guess this is probably a better description of it here, which is the average of these two values, x over y and y, where x is our initial input and y is our guess. So that is there. Average between guess and x over guess, where average sums the two values and divides them. The good enough function determines whether or not the process has come up with a guess that's close enough to the answer. And essentially all that does is it squares the current value of guess. So we say y squared and say, is that close enough to x? So if y squared minus x is pretty close to 0, so less than 0.001, then we'll say, sure, it's close enough to be a reasonable estimate of the square root of x. So we have a complex process built up out of primitives, combination, and ultimately abstraction. And the square root program shows us several examples of procedural abstraction in action. So recall that procedural abstraction means that we're going to hide the details of a process behind some meaningful name. So the user doesn't need to know how a procedure works in order to use that procedure. So for example, inside improve here, we can understand the body of improve without necessarily understanding how average works. We just know that in order to improve this guess, we're going to average that guess with x divided by the guess. Okay. Similarly, inside square root iteration, we don't need to know how improve works in order to use improve. We just know that we need a better guess, so we're going to call improve on the current guess, and we'll get a better guess out of it. So the user just needs to know the name of the function and the expected input to output mapping. The underlying process of how it makes that map can remain hidden without any complication. Now, there's several advantages to having procedural abstraction in our code. First off, it improves readability. So abstraction lets us say more with fewer statements, but also lets us be sure that we're saying the right thing when we say it. It's a lot easier to say average xy, for example, than it is to say divide plus xy by 2. And if we have to average things multiple times, repeating the word average is a lot easier than repeating that formula. And as you can imagine, if we had to write this entire program using only primitive operations, it would quickly become incomprehensible. So, as a program text moves closer and closer to the domain, the code becomes more expressive and more readable. Secondly, procedural abstraction facilitates modular design, that is to say, replaceable parts. So our definition here, for example, of square is square y is y times y. Okay. But we could have come up with many different definitions for square. So scroll down here, we have some here. So we have the input parameter multiplied by itself, or we have a combination of exponents and logs, or we could have come up with some recursive sequence of additions that ultimately calculates the same thing. Each one of these definitions would be equivalent at the domain level of abstraction. In order to actually square a value, they would all work, so they're all correct. So the fact that we have procedural abstraction allowing us to hide the details of the process from its usage means that we can separate the implementation of the process itself from its usage. We can have a bunch of different potential implementations. We can swap them out as needed. Perhaps we find a more efficient or a more correct implementation. We can swap it in place, replace this definition of square, this definition here of square, with a better definition, and the rest of the code wouldn't have to change. We could still just use the square function by calling it in our other functions. Right. One other thing to say about procedural abstraction is that it also hides the choice of parameter names. So for example, in our code we defined square to say square of the parameter y, but we could have just as easily said square of x, or square of z, or square of num, whatever we wanted. What this means is that the procedural abstraction, in order to have procedural abstraction, we need to have localized variable bindings. That is to say, we need to have variable bindings, specifically for the formal parameters, that exist within the function, but not outside of the function. And this brings us nicely to the notion of scope. So scope should be a familiar concept already, but there's a few definitions that I want to cover here, starting with the notion of variable bindings. So a variable binding is the association between a name or a symbol and some value. Now, as I mentioned before, in pure functional programming, variable bindings are considered to be constant. That is to say, once the binding occurs, that name or symbol is associated with that value until the end of its extent is reached and the variable gets destroyed. Okay. So this is a feature in functional programming known as referential transparency. It's something we'll discuss later on, but the general idea behind referential transparency is that each symbol in we'll say each variable is just a placeholder for the value that it's bound to. Okay, so another way of saying that is throughout our code, we could take all of the variables, replace them with their values, and the meaning of our code wouldn't change. Now we'll see what that means in terms of more complex code as we get further on in the course. But for now, I just want to introduce this notion of referential transparency. It means that our variables are constant. They don't change throughout time. Now, variable bindings exist only within a region of code that's known as that variable's scope. So the definition of scope is that it's the set of expressions for which some variable binding is valid. So for example, a procedure takes in some value, its arguments, and it binds that value to the symbols of its formal parameters. So the scope of that binding, of the parameter bindings, is the body of that procedure. Once the procedure is run and completed, those variables reach their extent and they get garbage collected and cleaned. It's also worth noting that a variable binding refers to a specific instance of a variable. Right? Each time a function is called, a new binding gets created for each parameter. So if I called this square function, for example, I said square x with the value 5, so I said square 5, then x gets bound to the value 5. But if I call square with the value 6, for example, we create a new instance of that binding where this same symbol x gets bound to the number 6. Right? So each time we call a function, we're creating new bindings for each one of those parameters. So these bindings refer to specific instances of variables. All right. So the set of all active scopes at any given point in a program is known as the environment. Scroll down here. There we go. So the environment defines the context of evaluation. So if we have some expressions, we need to know the value of them. Like for example, if I want to know what's the value of the expression x plus 1, well, that depends on the value of x. And the value of x is dependent on its binding within the environment, right? If we want to look up a name, right, if x has the value 5, for example, if we say x plus 1, we get 6. If x has the value 10, we get 10 plus 1 is 11. Okay? So in order to evaluate any expression, we need to do so within some sort of context, some sort of environment. So you can think of the environment as the database of all of the variable bindings that exist within our code. Okay. So we've seen a bunch of different types of scope already. We've seen the primitive scope, which is provided by the language itself. It contains bindings for all sorts of built-in operations like addition, multiplication, absolute value, the different type checking predicates, etc., etc. We've also seen the global scope, which is the top-level user scope, corresponds roughly to the main file or a single program. And this is, for example, where we would have defined square root and all of these things if we had opened Dr. Racket. And we've also seen local scopes. So in Scheme, local scopes are only constructed by procedure application. I'll leave an asterisk next to that because we'll see situations where it seems like that's not true, but it is true. The only time we create a new local scope is when we create a new procedure and run that procedure. Okay. So local scopes contain all the different parameter bindings, and these parameter bindings only have meaning within the body of that function. Once the function's done, those scopes disappear and all the variables in them as well. So from our square root example, where is an example here? The average in y, for example, can't be used inside improve. And the symbol x in average is different than the symbol x in improve because they are localized to just those functions. All right. So in Scheme, functions can be defined within other functions. This is something called block structure or nested functions if you prefer. So consider, for example, our square root program. And let's actually take this code and put it in Dr. Racket finally. Copy and paste. And we can run our code, make sure it works. Square root of 25 gives us something relatively close to 5. Good. Now if we want to use block structure, it's pretty straightforward to transform. We just take the header line of our main function, square root here. We put it up at the top of our code, so square root. And we take all these other functions and indent them to say that they're inside. And because this is taken from a web page, a little bit of cleaning on the indentation, and there we go. Now the definition of square root starts by defining all of these other helper functions and then calls one of them. And it's worth pointing out that we have all the same functions, but they're all just defined within square root. We didn't change the definitions of any of them, and they all still work fine. Can test that by running our code. Call sqrt25 again, and we get a similar answer relatively close to 5. Now one thing to point out about this though is that the scope of all of these nested functions, that is to say the region where these functions like square and good enough are valid, is now limited to the local scope of the square root function, this highlighted space here. Outside of this, we can no longer ask, for example, square 3. Square is no longer defined because it's defined locally inside this square root function. Yeah, so there's a few advantages for why I'd want to do this. The most obvious one is information hiding. It limits the amount of namespace pollution in the global scope. You can imagine, for example, if our square root process here was a small part of a large program, by using all these other functions to help construct our square root process, we're reserving these names. If we define them in the global space like we did before, we can no longer define anything else in the global space that has the name improve or the name good enough without causing some sort of conflict of naming here. And you can imagine names like improve or good enough are pretty general names that might apply outside of this square root. So by tucking them inside, by having this nested or block structure, what this means is these names are now reserved to just inside the square root function, and outside the function they're no longer reserved and they can be reused without any conflict. Right, and it's also it's a good idea in terms of abstraction, right? We defined 5 or 6 different processes here, different functions here, square root, square, and all these, but the user only really cares about one of them. They only care about square root. The user doesn't care about all the different parts that go into calculating square root so long as we can get a solid estimate of a square root. So it doesn't make sense to expose all of these other functions if they're unnecessary, so we can hide them away as part of the unnecessary to understand process, and the user of square root can still do what they would do without knowing all the bells and whistles on the inside. Now, one thing I want to point out about block structure here is that when we have internal defines like this, define statements within a define statement, these things should be placed first in a procedure. Okay. Now, from the textbook says, here, I quote here, "The management is not responsible for the consequences of running programs that intertwine definition and use." Which is to say, if you use code that does stuff like perhaps something like a display hello or something like that, or maybe it has some calculations and then does some more defines, your code might work, it might crash. It's implementation dependent. Okay. From what I've seen in Dr. Racket, it's mostly okay, but you will lose some portability to other scheme implementations. Also, your code will become harder to understand. So I highly recommend, if you are using block structure, as you will be, always put your defines as the first thing in your structure, and then the very last thing will be the actual body of that function. So if we have nested functions, that means that we have nested scopes. So just like how local scopes are nested inside of the global scope, we can have many local scopes, each nested inside of each other. So let's take a look at this on a whiteboard here. Let's go, let's draw some squares representing scopes in our code. So using this square root example, we have this scope here, which is the square root block of code, and this contains definitions for all these other things, square, good enough, average, and all those, but it's defined inside of another scope known as the global scope. And as far as our code is concerned, that's the only definition in the global scope. Okay, but the global scope is defined inside of another block that maybe I should have left some more room for, known as the primitive scope, and that's the top level scope defined by the language itself. Okay, so inside primitive, we defined the global, or the user-defined global happens automatically. Inside that, we defined the square root function, and inside square root, we defined all of these other procedures. So square root has storage for the variable x here, so let's put the letter x. It also has storage for the function square, which has its own scope. So we'll draw a box for that. Has storage for the function good enough, so we'll draw a box for that. It has storage for the function average, and that has its own scope because it's a function. And we have improve, and one more square root iteration, sqrt iteration. Okay. So each one of these boxes represents a scope, and inside there we have storage for variables, like if we define square y, this has storage for the variable y. Good enough has storage for the values guess and x, etc., going down the list. Okay, so we have all these things stored in this sort of nested scoping block structure. Now, in Scheme, the nesting of scopes matches the nesting of code blocks, which makes it pretty easy to keep track of. This is what's known as lexical scoping, because the scopes match the code itself. We'll see other types of scoping as we go throughout the course, but for now, lexical scoping is pretty straightforward. It's because square root has square defined inside of it, the scope for square is defined inside the scope for square root. Okay. Now, this brings us to the notion of free variables. So the scope of a variable is going to span all of its nested scopes. That means we can use variables from enclosing scopes within the nested blocks inside their scopes. So think if we have a global variable, for example, it's pretty straightforward that we can use that inside of a function, something you've probably seen before. It's like that now, but with many more layers of local scopes inside each other. So these variables are called free variables. So a free variable is one that is used within a scope in which it's not defined. So a non-local variable is another way of thinking of it. So let's take a look at a simple example here. Let's go to Dr. Racket. So define a function called foo of a. And within that function, I'll define another function called bar of b. And inside that, I'll say plus ab. So the definition of bar b is a plus b, where we have some parameter b, but what is the value of a? And then we need the body for foo, so we'll say bar of times a2. So question is, what is the value of this expression? Take a minute, pause the video, take a look at what you think the answer is, and then we can walk through the substitution model here. Okay. So inside this function bar here, we have two variables, a and b, but b is the only local variable, right? This is the scope of all the parameters, of which b is the only parameter for bar, which means a is not defined locally, but it is still used. And we can see that it is defined inside the enclosing scope for foo, which is to say a is a free variable inside bar. So a substitution model for foo3 would look like this. Start with the keyword, or start with the expression that we typed in, so foo3. And then we evaluate the two sub-expressions. So foo is the function that represents all of this, and 3 is the integer 3. So they're about as simple as we care to make them, and we do the substitution step. So we say take the body of foo, which is all of this, and we'll put it all in one line here, just to stick with substitution model conventions. Okay. And then we substitute the value 3 for a everywhere in this code. So this becomes a 3, and this becomes a 3. And this is sort of a key point here, is that the a inside bar has already been converted to a 3. We can do this because we can assume that a is never going to change. It's a free variable. We'll talk about situations where maybe we shouldn't do this, but in this specific situation, it's fully allowed, and the meaning of the code won't change. So what happens next is the first part of foo the first part of, the body of foo, which is to define bar. Now, defines are somewhat invisible to the substitution model. They happen, they affect the environment, they create a binding between the symbol bar and the function that will ultimately add 3 plus bar as argument. But to the substitution model, essentially, what happens is the define line occurs. There we go. The define line occurs and then disappears. So what we're left with is the remainder of the overall expression, which is bar of 3 times 2. Okay. Now, with applicative order, we need to evaluate times 3, 2 before we can do the substitution, so we get bar of 6. And then on the next line, we say substitute 6 into the parameter for bar, which is b, inside the body of bar. So the body of bar now looks like this, plus 3b. So we copy that, where b now has the value 6. And then it's pretty straightforward. 3 plus 6 is 9. So the key point here is when we're doing the substitution, when we have that free variable, that substitution occurs everywhere in the body of foo, including inside nested bodies within nested functions. Okay. Now you can usually omit function definitions from the substitution model without loss of clarity. I included it here so that we can see very clearly why that value gets substituted. But you can usually, because they don't really change much, not have to write them. You can go from foo to the body of bar, and then just remember when you're executing the body of bar that a should in fact have its original value. Okay. As another example, going back to our square root code here, this variable x can now be a free variable within all of its nested functions. This will allow us to simplify some of the functions. So in the original code, we are passing x from the user into square root iteration without changing it at all. And then square root iteration passes it into good enough, and it passes it into improve, and passes it into itself on subsequent steps as well, all of which unchanged. It's just the original outer value of x, which is to say we can get rid of this. We don't need to pass x into square root iteration or improve nor into good enough as we had to before. So we can actually get rid of this here. We can get rid of it here, and we can get rid of it here as well. That means we don't have to pass it into good enough here, nor into improve here, nor into square iteration here. So what happens when we need the actual value of x? Well, the value of x is needed, for example, in improve to do the quotient for the new value of our improved guess. It's also needed to determine if something's good enough. When we square our guess, we need the original value to see if the guess squared is equal to the original number. But that's not a problem anymore because x in these functions, inside good enough and inside improve, is now a free variable. Okay. Now there's a bunch of other free variables throughout this code. So for example, square. Square is a symbol that's used within good enough, but is not defined within good enough. If we want to know the value for that, we look locally, we don't find it. We go into the enclosing scope and we find it within within square root. Similarly, with all the arithmetic operations and the built-in functions, abs, less than, divide, plus, all of that is defined within the primitive scope, which, as we saw in the previous drawing, is just an enclosing scope from where we currently are. So if we need abs inside, what was that? The good enough function. Oh, there's the good enough function here. That's inside square root, which is inside global, which is inside primitive. And that primitive scope is where all of those things would be defined. I didn't include it here because it would be an exhaustive list and fill up the diagram pretty quickly. But as you can imagine, if we're inside this good enough function, we ask what's the value of abs. We just go through the enclosing scopes until we find something. If we make through all the enclosing scopes without find it, then it doesn't exist and we can say there's a name error. Okay. Now, going back to the code here, we also have an x inside average here. So this variable x is not a free variable, right? It's declared locally as a parameter. So that is not something that's going to take on the value of x. This has its own local value of x that effectively overrides or hides the free variable x from the enclosing scope. This brings us to the notion of scope and visibility. So scope, as I mentioned, is the set of all expressions for which a name is bound. The visibility of a variable is where that variable can be seen or reached. The key difference here is that we can hide the values of free variables by including local ones in our definitions. So if we define a variable in some local scope, like we did inside the average, let's go back to our code here. So inside average, we defined a local variable x. This now hides the free variable x. Within the scope of this function, we no longer have access to that free variable. Because if we ask what is the value of x, well, we'll find the answer locally as the parameter x. We won't then continue our search and also find it in the enclosing scope. So this is the visibility. So the visibility of this variable x is the entire scope of x, so all of the space, minus the places where we've defined local x's, so minus this little block here. Okay. All right, let's go on then to a bit of practice here. So I'm going to define a function here, and then I'll ask you guys what's the output. Now, I can't hear you, so I'll let you determine if you can figure out what the output is before I explain why the output is as it is. So first off, let's define a function g of x, and inside that function I'll define another function f of y, and say plus xy, and plus f3, f4. Now, what is the value of the expression g at 5? So obviously you can type this in and run it and get the answer, but walk through it manually, get a pencil and paper, see if you can't understand what the value should be before you find out what the value actually is. All right, so walking through this code, let's actually just do the substitution model for this one again. So substitution model goes g of 5. And now again, we have a function and an integer. It's about as simple as we can make it. So we go to the next line, which says substitute 5 for x everywhere in this block of code. So copy, paste, and put it all on one line. Okay. So x here gets the value 5, so we have a 5 there, and that's the only x throughout the code. Now that sort of happens and then unhappens in our substitution model because we set the value 5 inside the body of this function, but then the define happens and the next line says, okay, great, that define exists, let's evaluate the rest of our expression. The rest of this expression says add up the result of these two things. So before we can do that addition, we have to evaluate all of the sub-expressions. So what is f of 3? Well, to get f of 3, we do the substitution. So we have plus, and then the body of f, which is this, where x is substituted for 5 and y now has the value 3. And just to save us some time, I'll do the same on the other side. We get plus 5, 4 for the call to f4. So because these are two independent calls, their values aren't dependent on one another, so we can evaluate them at the same time. All right, and then from there we can just reduce everything. So we get plus 8, 9, and ultimately 17. Okay. So again, the key here is that when we do the substitution and we have free variables, that substitution occurs even inside those nested scopes, even where that variable is a free variable. We can run our code and verify our answer. We get 17, and we're good. All right. Yeah, let's do one more example for this video. Oops. So let's define, what's this one called? Outer x, and inside that we'll define a middle y, and inside that we'll define a deliberately confusing inner x. Okay. So a real simple function plus xy inside inner. For middle, it will define inner, and then it will say inner of plus xy again. And for outer, we'll just say middle of plus x1. Okay. So what is the output if I say outer 3? Again, pause the video, see if you can figure it out, and then we'll walk through it together. So the key point to this is that the nesting, or the depth of the nesting, can go to any level. There's no limit on, there's no syntactic limit, at least, on how deep you can make this code. So you can nest functions within other functions within other functions. The only real limit is how far you can go before the whole code starts to not make as much sense. So in this case, we have 3 levels of nesting. We have outer. Inside outer, we've defined middle, and then we run middle. And then for the body of middle, we say define inner, and then run inner. And then the body of inner is just an addition. Okay, so sort of back and forth through the code here. So it starts at the top, defines these things, and then runs middle, defines some things, runs inner, defines inner, and then runs a body. So the output here starts at 3. So 3 goes into x. And now this x is a free variable throughout the body of middle, but not the entire body of middle, because inner defines its own variable x, which hides the global variable x. So when we say plus xy here, we're referring to the local variable x. When we say plus xy outside of inner, we go looking into the current scope, the local scope, which is middle. Middle doesn't have anything defined as x, so we go to the enclosing scope, and we're using the outers version of x here. Similarly, inside the body of outer, x is just a local variable. So to walk through this, we have outer 3 goes into this x, and we do all this definition stuff, and we say run the function middle on the value 3 plus 1, which is 4. So we get middle where y gets the value 4. That again says do some definitions and then run this code. So it says plus xy. And we know y is 4 because that's local. We can't find a local x, so we use the outer x, which is the same as it was before, which is 3. So we get plus 3, 4. Okay. Now, if we add that up, we get 7. 7 goes into inner as x, and that says plus xy again. Now, if we go looking for the symbol x, we find it locally with the value 7. We go looking for the value y, we don't find it locally. We do find it in the enclosing scope with the value 4. So we have 7 plus 4, which should give us 11. Run our code, and that's our answer. All right, so a lot to unpack here. Make sure you understand all of these parts. We will be building on them in future videos and throughout the course. And I will see you guys in the next video.